Hi, welcome. And now we're looking at Advanced Math, Chapter or Unit 12, Part A, Page 5. Some examples of graphing planes in a three-dimensional coordinate system. So example number one, we have the equation 2x plus 3y plus 4z equals 12. And what we're going to do is, again, we're going to find the places where that plane crosses the x, the y, and the z axis. So first of all, if we want to locate where it crosses the x-axis, that happens when the y and the z are 0. So for the x-axis, we can write a little equation, um, 2x equals 12. That's setting the y and the z terms to 0. So that solves to x equals 6. So if we count out 1, 2, 3, 4, 5, 6 on the x-axis, that's the x-intercept for our plane. For the y-intercept, we're going to solve the same equation with the y term, with the x and the z terms taken out. That's going to be 3y equals 12 because on the y-axis, the x and the z are both 0. So we solve that one for y. We get y equals 4. Count out 1, 2, 3, 4 on the y-axis, and there's your y-intercept. On the z-axis, that intercept happens when x and y are equal to 0, so we get the equation for z equals 12. Solve for z, you get z equals 3. 1, 2, 3 on the z-axis. So those are the three intercepts for this plane. And to represent that plane graphically on this three-dimensional grid, we connect those intercepts together with line segments, forming a triangle. And then we shade it to give the impression that it's not just a triangle, it's the plane bounded by those three edges. And that's actually all we need to do. And always remember, though, that this is a plane which is infinite, and that means that the edges, they're not really edges, it's just a graphical tool to give you the impression of the orientation of the plane. In reality, the plane continues on infinitely in all three directions. We just really can't effectively draw that. All right, next example. 5x minus 2y plus 2z equals 10. So we'll do the same thing, axis by axis. X-axis, we're going to be solving the equation 5x equals 10 because y and z are 0 at that point, so x equals 2. For the y-axis, we're going to be solving the equation negative 2y equals 10, so y equals negative 5. So we're going on the y-axis, we'll count to the left of the origin, 1, 2, 3, 4, 5 units. And for the z-axis, we're going to be solving the equation 2z equals 10, or z equals 5. So we can count up 1, 2, 3, 4, 5 units on the z-axis. And so we have the 3 points, which we can connect together with segments and shade in the middle. So we have this um, tortilla chip sitting in our three-dimensional axis system. Again, giving us the impression of the orientation and position of the plane, but not all of the plane, because we can't show the extension of it outside the edges of the triangle. The third example, this is some challenges. So here's an equation, very simple, y equals 4. If you were drawing that or plotting that in a two-dimensional space, you would draw a horizontal line that crosses the y-axis at y equals 4, or coordinate 0, 4. And it works the same way here. The place where this plane crosses the y-axis is at the y equals 4 point, so it crosses there. What it means is, again, this equation represents all of the three-dimensional points that satisfy the equation. So there's no constraint on x and there's no constraint on z. We're only saying that y has to be equal to 4. So for example, that means the point like 1, 1, 0. So this point, which is at x equals 1, y equals 4, and z equals 0, satisfies the equation y equals 4. this point does, this point does. All the points along here that have a y coordinate of 4 and different values of x, they satisfy the equation. And you can go into the negative x values as well. They'll all satisfy the equation. Or if you started at this y equals 4 point and did a vertical series of dots, so the point where y equals 4 and z equals 1 and x equals 0, that would satisfy the equation. All of these points going vertically from this intersect would satisfy the equation. So, and we could go, this is again making a plane, so is an infinite number of points. We've drawn a set of points that are parallel to the z-axis, another set of points parallel to the x-axis. How do we represent this? That's actually kind of a challenge. So in a situation like this, what I would draw is sort of a rectangular section of the plane with edges that are parallel to the x-axis. Here's an edge parallel to the x-axis, and here's another edge parallel to the x-axis. And the other pair of edges are parallel to the z-axis. And I've got a point highlighted here at the center where this plane crosses the y-axis. And I could, similar to the other plots that I've done, fill this in with some cross-hatching to suggest that, yes, it's a plane. But as before, we know that in reality, this plane continues on infinitely in all directions, like that. So it's like when we did a couple of pages ago, a sort of a drawing of a room inside this x, y, and z coordinate plane. This is like a wall of a room. Um, you may or may not have success kind of visually seeing this, but that's the best we can do. So again, this is a plane, crosses the y-axis here, never crosses the x-axis, and it never crosses the z-axis. So finally, for the last example, let me rewrite this in a more of a standardized form. I put everything on all the variables on the left-hand side. We'd have y plus z equals 3. Now, that's actually a two-dimensional equation. And we can solve for the y and the z intercepts if we want to. The y-intercept is going to happen when the z is equal to 0. So that would give us the equation y equals 3. The z-intercept happens when the y is equal to 0. So that would give us the equation z equals 3. And that defines the y and the z-intercepts. Now, if we wanted to, we could draw a line passing through those 2 points that would satisfy this equation. And because the x isn't in this equation, it means that as long as this relationship is true, the x can be anything at all. So we could imagine continuing these points in a direction that's parallel to the x-axis, and we actually get a family of these lines all parallel to each other. All the same distance away from the x-axis. They'd all have the same sort of relationship here with the x-axis. And how to represent that. So just on the example over here where I drew a plane, a section, a rectangular section, we could attempt to do something similar here. I'll do it in red, draw a rectangular section and shade it in. That's one way. And there's no perfect way of doing this. That's why these are called challenges. It's difficult to represent graphically a plane in 3 dimensions in a 2-dimensional drawing. It is difficult. So that's why these are challenges. These are two possible interpretations of that. If you don't see it, doesn't really click for you, don't worry about it. It's not a central issue for the unit. You do want to make sure that you've got a good handle on how to do these. These ones, these are more straightforward. These are challenges. They're cases where your plane is parallel to one or more of the axes in the system, and they can be difficult to represent. All right, that's the last page of Part A. Next, Part B.